Let's talk about chaos and differential equations. Some things can be predicted way in advance, like the solar eclipse of April 8th, 2024. I traveled to southern Indiana to see it. It was amazing. The sun was a big black disk in the sky surrounded by a halo. You could look at it without glasses, without sunglasses or special filters. And it was about as dark as it is at dusk, even though it was 3 in the afternoon. Really just an incredible sight. It's going to be an eclipse on September 14th, 2099 that will pass over the Chicago area. I don't think I'm going to make it to that one. But some things cannot be predicted way in advance. For example, why are there no 21-day weather forecasts? 14 days is about as good as it gets. The Wikipedia page about Tom Skilling, retired weatherman who used to forecast weather in Chicago, notes that he also predicted the 2011 Chicago blizzard in January, 2 weeks before it hit Chicago. That's why he's such a weather stud, because he could predict a blizzard 2 weeks in advance. Predicting an eclipse 2 weeks in advance is not such a big deal. We can show mathematically why there are no 21-day weather forecasts. Let's look at the equation y equals kx times 1 minus x for different values of k. Let's start with k equals 2. So we have y equals 2x times 1 minus x. We plug in a value of x between 0 and 1. Whatever the output, we plug that back into the function. And we do that again and again and again. Here's the easiest way to do this on the TI. So say x equals 0.3. Type 0.3 and press enter. Then type 2 times answer times 1 minus answer and press enter. And just press enter repeatedly. Basically, that's the calculator's way of taking whatever your output is and plugging it back into the function 2x times 1 minus x. So I get 0.3, 0.42, 0.4872, etc., etc., etc. And then eventually it's just 0.5. Let's try a different value of x, like x equals 0.1776. Type 0.1776 and press enter. Then type 2 times answer times 1 minus answer and press enter. And just press enter repeatedly. I get 0.1776, 0.292, 11648, blah, 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 blah. And then eventually it's just 0.5. Any value of x between 0 and 1 leads you to 0.5, which is called an attractor. An attractor is a number that the sequence zeroes in on. Now let's try k equals 3. So we're not changing the value of x, we're changing the value of k. We're looking at k equals 3. We plug in a value of x between 0 and 1. Whatever the output, we plug that back into the function. We do it again and again. Let's say again x equals 0.3. Type 0.3 and press enter. Then type 3 times answer times 1 minus answer again. This is why we have 3 times answer times 1 minus answer. And press enter. And then press enter repeatedly. I get 0.3, 0.63, 0.6993, blah, 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 blah. The numbers alternate between about 0.68 and about 0.64. These are the two attractors. The numbers do not zero in on just one number like they do when k equals 2. Now let's try k equals 3.5. So y equals 3.5x times 1 minus x. We plug in a value of x between 0 and 1. Whatever the output, we plug that back into the function again and again. Okay, so again, say x equals 0.3, type 0.3 and press enter. Then type 3.5 times answer times 1 minus answer and press enter. And press enter repeatedly. Rounding to 4 decimal places, this is what I get. 0.3, 0.735, 0.6817, blah, 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 blah. The numbers get closer and closer to 0.3828, 0.8269, 0.5008, and 0.8749 roughly. I mean, rounded to 4 decimal places. These are the 4 attractors. The numbers do not zero in on just one number like they do when k equals 2, and they don't even zero in on, they don't even bounce between 2 numbers. They bounce among 4 numbers. Now let's try k equals 4. Y equals 4x times 1 minus x. So plug in some value of x, and whatever the output, plug it back in the function, do it again and again and again. So again, try x equals 0.3, type 0.3 and press enter. Then type 4 times answer times 1 minus answer and press enter repeatedly. Rounding to 4 decimal places, I get this, okay? The numbers bounce around seemingly randomly. There are no attractors. The numbers do not zero in on just one number. They don't even bounce between 2 or 4 numbers. This is chaos. Chaos is deterministic behavior which appears to be random. Again, it's deterministic, it's predetermined, but it just looks random. For y equals 4x times 1 minus x, starting with x equals 0.3, we get the sequence 0.3, 0.84, 0.5376, blah, 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 blah. That last number in the sequence, 0.7472, is the 40th number in the sequence. What would the 40th number in the sequence be if instead of x equals 0.3, we had started with x equals 0.301? That's pretty close to 0.3. You might think it might not make a difference. We end up with 0.3706. That's very different. So even though we started with a number that was pretty close to 0.3, we ended up with a number that was very different from 0.7472 by the time we got to the 40th number in the sequence. What if we started with x equals 0.3001? 0.9400, again, very different from 0.7472. Okay, let's try this one. 0.30001. That is really close to 0.3. Surely that's going to give us a number close to 0.7472. Nope, not even close. How about this one? X equals 0.300001. That is so microscopically close, infinitesimally close to 0.3, that by the time you get to the 40th number in the sequence, it should be pretty close to 0.7472, right? Nope, not even close, 0.0293. How about adding another decimal place? Do you think that's going to make a difference? Nah. No, 0.9020, not even close to 0.7472. For y equals 4x times 1 minus x, if we start with x equals 0.3, then 0.7472 is the 40th number in the sequence. If we start with this number, then 0.9020 is the 40th number in the sequence. A small change, a tiny, tiny change in initial conditions leads to a dramatic change in the outcome. By contrast, for y equals 2x times 1 minus x, if we start with 0.3 or 0.4 or 0.9 or 0.1, then 0.5 is the 40th number in the sequence. Changing the initial conditions generally has no effect on the outcome. Weather is like this first scenario and not like the second scenario. Edward Lorenz, a mathematician at MIT, Massachusetts Institute of Technology, tried to predict weather based on temperature, air pressure, wind speed, etc. Here is the system of differential equations he came up with. So suppose we have a two-dimensional cell, a region that is warmed from below and cooled from above. Dx dt equals sigma times y minus x. Dy dt equals rho x minus y times minus xz. Dz dt equals negative beta z plus xy. Here x is the rate of convective overturning. This occurs when air rises because the air above is cool and the air below is warm. It produces wind and thus affects wind speed. Y is the horizontal temperature variation, and z is the vertical temperature variation. This is a pretty simple model. We have much more sophisticated models nowadays, but this is just what he started with. Lorenz ran calculations one day, then did more calculations the next day, starting in the middle of the previous day's calculations. Here's what Lorenz obtained. The second day's calculations began to diverge from the first day's calculations right about here. Why? The computer stored data accurate to 6 decimal places, like 0.123456, but when he picked up where he had left off, he had entered data accurate to only 3 decimal places, like 0.123. He figured that, 3 decimal places, that's good enough. It's not going to make a difference. But it did make a difference, huge difference. Accurate long-term weather forecasts are impossible because our measurements of important factors like temperature, wind speed, etc. are measured only so accurately. Because if measuring something to 3 decimal places is not sufficient, there's no way you're going to get an accurate weather forecast. Maybe initially it'll be accurate, but eventually it's going to diverge. This is an example of what Lorenz called the butterfly effect. A butterfly flapping its wings in Brazil could cause a tornado in Texas eventually. The technical term for this is sensitivity to initial conditions. Weather is sensitive to initial conditions. A tiny change in temperature could have a dramatic impact on weather, not initially, but eventually. That's why our meteorologists do not go any further than a 7-day forecast.